So this is only a brief history. Brief history means it is not that much old also. This evolutionary computation is not that much old. So actually it was started in the 1950s. The idea of using simulated evolution for solving engineering as well as design problems have been around since the 1950s. This is taken from the reference, that is Vogel 2000, that is reference. Then it was started like the papers works from Bremerman in 1962, then Box 1957, then Friederberg 1958, etc. These works actually, these were mainly focused on problem-specific works. For a specific problem, they developed a specific algorithm, etc., etc. It was not a generalized thing. Then in 1960s, three different forms of evolutionary computations emerged, and this particular statement is taken from this Baek et al. It is published in 1997. So the three different forms of this evolutionary computation are the evolutionary programming, then genetic algorithm, and evolution strategies. Out of which this evolutionary programming and evolution strategies, these are actually generalized forms of this simulated evolution, which was introduced earlier. And genetic algorithm actually it incorporated, or it tried to incorporate a generalized procedure for solving all the problems, all the design as well as engineering problems. So that is the difference between evolutionary programming and evolution strategies. In evolutionary programming as well as evolution strategies, most of these methods were specific to each of the problems. Then even though the genetic algorithm were started in 1962, the first available publication is, if I remember it correct, it is in 1970s. So then the designers of each of the EC techniques, that is evolutionary computation techniques, so that their particular problems could be solved via simulated evolution. So these evolutionary computations were developed for solving particular problems, not a generalized problem. So as an example, this Vogel was concerned with solving prediction problems, or predicting something or forecasting something. So then Rechenberg and Scheffel were concerned with solving parameter optimization problems. As I said earlier, the problems, these methods are mainly used for this optimization methods. So Rechenberg and Scheffel were concerned about the parameter optimization problems. Then, but Holland was concerned with developing robust adaptive systems. That is, any problem can be solved using this particular method. That was the concept of Holland. So Holland is the one who introduced this genetic algorithm. So it was tried, or it was in order to solve all the available problems, all the problems which cannot be solved using our conventional or classical solution methods. So that is the condition. Then each of these researchers successfully developed appropriate ECs for their particular problems independently. That is, these different researchers, these three categories of researchers actually developed their own algorithms or their own evolutionary computation procedures for their own problems. In the US, the genetic algorithms have become the most popular EC technique due to a book by David E. Goldberg. That is, this particular book is in our reference list also. That is the book by David E. Goldberg, that is Genetic Algorithms in Search, Optimization, and Machine Learning. In our syllabus, this book is of importance because it is in our reference list. Actually, this book explained the concept of genetic search in such a way that a wide variety of engineers and scientists could understand and apply this. Because of this particular book, most of the people understood what is a genetic algorithm and how it can be applied to problems on which they are working. So actually, it is in this book was published in 1989, and the use of genetic algorithm for solving optimization as well as design problems started to increase. The use of this one started to increase after this 1990s, that is after publishing this particular book. Then after that, there were a number of books which were published to help the fueling this development, the growing interest in this evolutionary computation. Some of them are the Lawrence Davis book, that is Handbook of Genetic Algorithms, which was published initially in 1991. Then there is Michaelowicz's book that is published in 1992, Genetic Algorithms plus Data Structures equal to Evolution Programs. Then there is another one by Cosa, that is genetic programming, that is also in 1992. Then there was a book published in 1995, which is authored by Vogel, Evolutionary Computation Toward a New Philosophy of Machine Learning, Machine Intelligence. So these four books, again, fueled the growing interest of this evolutionary computation. But the other important aspect that happened because of these books is the differentiation between this EP, that is evolutionary programming, evolutionary strategies as genetic algorithm concepts were brought together. The difference between these were reduced. So what happened is an explosion of new and exciting forms of evolutionary computation started coming up. So this these different types of evolutionary computation techniques were classified into three different generations. Whatever is developed till now is categorized into three different generations. The first generation is this evolutionary programming by Vogel, then genetic algorithm by Holland, and evolution strategies by Reichenberg and Scheffel. These were problem-specific strategies. For a specific problem, a specific strategy was developed. For another problem, you have to develop another strategy. So that sort of thing happened. In the second generation evolutionary computation, what happened is in the structure of the problem also there is some development happened, like genetic evolution of data structures, then genetic evolution of programs, then hybrid genetic search, taboo search, a new evolutionary computation methods, taboo search was also developed. The main authors for this generation, this second generation is where this Michaelowicz, Cosa, Davis, and Glover. So these type of new techniques started to evolve in the second generation EC. Some of them were specific to some specific type of problems, and some of them were generalized method which can be applied for many different problems. And the third generation, the different elements or different types of evolutionary computation systems that came in the third generation is artificial immune systems, cultural algorithms, DNA computing, ant colony optimization, particle swarm optimization, memetic algorithms, estimation of distribution algorithms, and the list actually goes on. Goes on means if you search for evolutionary computation techniques or this nature-inspired algorithms, if you search for nature-inspired algorithms in Google, you may end up with more than 100 different types of algorithms, like gray wolf algorithm, frillhead algorithm, this artificial bee colony algorithm, so on. So there are so many different types of algorithms are available. All of them belongs to the same third generation evolutionary computation methods. And all these methods can be used for solving different types of problems, not just one type of specific problems are not addressed by these methods. This can be tailor-made, or this can be what you say tweaked in such a way that you can make these problems work for solving almost all available problems in available problems which cannot be solved using our conventional methods. So that is the concept. Then we don't know what will happen in the fourth generation, because it is till now what we have seen is only third generation. We may see better algorithms which may use the hardware capabilities, etc. in the fourth generation. I don't know what will be happening. Now, once you understood what is evolutionary computation, how it is working, and the history, the development of evolutionary computation, etc., etc., let's walk through an example. That is how evolutionary computation is used to solve complex problems. Let's see. So let's say when you were asked to solve the following problem, that is, you were asked to solve a function, maximize. The problem is to maximize f of xy. F of xy is any function. And the function is given as, it is written in two different forms. One is this one, 0.5 plus sine square root of x squared plus y squared, the whole squared. The whole squared is for including the sine. In order to understand this particular statement better, I have written it in the equation form itself towards the right. So sine of square root of x squared plus y squared, the whole squared, minus 0.5, then divided by 1.0 plus 0.001 x squared plus y squared, the whole squared. So this is the function. This is the function that you have to maximize. And the range of x and y are taken from minus 100 to plus 100. That is, the value of x and y goes from minus 100 to plus 100. Now what you must do is you have to find a solution that is greater than 0.99754, and you can only evaluate a total of 4,000 candidate solutions. So you have to evaluate 4,000 candidate solutions, and you have to find out a solution for this particular condition. And the solution must be greater than this 0.99754. That's the condition. So how to solve or find out the value of x and y? You can put any value of x and y in this equation, and you will get obviously a specific value for f of xy. That's obvious. If you put x as minus 100 and y as plus 100, you will get a specific value for this condition, and that value can be taken as f of xy in that for that particular combination of x and y, that is minus 100 and plus 100. Then you can take x as 1 and y also as 1. That is also a possible solution. So when you put x as 1 and y as 1, you will get a specific value for this one. So that way you will get a different combinations of values are possible. You doesn't know which combination of x and y will give you the maximum value of f of xy. That is what you want to find out. Now, if you plot this particular function, in a three-dimensional plot, that is x is in this direction and y in this direction, and f of xy in the z axis. If you plot it like that, the plot will be something like this. You doesn't understand anything, because when it is towards minus 100, when both the x and y are towards the minus 100 part, then that value, that is somewhere here. So that sort of value will give you somewhere around 0.5. And when it is towards this condition, that is plus 5, plus 100, both values plus 100, then also you will be getting somewhere around 0.5. Then minus 100 and plus 100, x is minus 100 and y is plus 100, that also you will be getting the same 0.5. But when the value tends towards the middle, that is when x and y are somewhere around 0, the maximum value is happening. We doesn't know at what value of x and what value of y the maximum is happening. The maximum value of this f of xy is coming up. That can be made available only if we plot all the values, all the possible values in this region. And if we fix a specific value for y, that is, if we put y as 1, and then we plot this particular value, function, in that case only x is varying from minus 100 to plus 100. So in that case, the maximum value, say it is close to 1, That is happening at around when it is x is 0. So x is when x is 0, this value, the value is maximum only in this condition. At this when y is fixed, when y is fixed value, that is y is fixed as 1, and when we are varying x, then in that case the value of f of xy will be varying like this, when from 0.5 to some value, that is then it is like an oscillating signal. Then the maximum value will be somewhere here, that is at x equal to 0. So that is the condition. So by this you might be getting that x equal to 0 as well as y equal to 1 is a possible option, possible solution for this particular given solution, given problem, that is maximizing x equal to 0, I mean maximizing f of x, the given function. So then how to develop an easy, that is evolutionary computation for this following problem, that is our condition. Now an individual, that is a chromosome or a candidate solution, all these terms are synonymous, that is an individual in a population, or a chromosome in a population, or a candidate solution in a set of solutions, etc. are the same thing in evolutionary computation. In genetic algorithm also it is the same. Now, it consists of, an individual consists of two values, one value for x and the other value for y. So it can be, as I said, it can be say 1 and -1, -1 and 1, 0 and 0, 0 and 5, etc. Any possible combination of x and y from -100 to +100, that is an individual. Now the fitness of this particular candidate solution is found out using this, by evaluating this f of xy. That is the function that is already given to us. We are putting the value x and y in that particular function, and then we get a specific value for that particular function, I mean function. So that value is the fitness. So the fitness of this particular value is the function itself, the function when you are getting the value of the function. So that is the fitness. Then this is the possible procedure, the procedure for this simple evolutionary computation. We initialize that the what you say, the number of trials, or I mean not the number of generation. The first generation we initialize it to be 0, that is the t is 0. Then we initialize the population. The population, as I said, a number of randomly generated solutions. The solutions is xy, a combination of x and y is a candidate solution. So a number of different solutions are generated. Number of different solutions are generated randomly. Randomly means between -1 and -100 and +100 we generate a specific value for x. Then we generate another specific value for y, again within the same range, that is -100 to +100. So that particular combination creates a specific solution, a specific candidate solution, or a specific individual. So a number of such candidate solutions are generated to form the population. So we initialize the population. The population for the first generation is initialized pop t equal to 0 at t equal to 0. Then we evaluate each of these elements in the population. Each of the elements, each of the candidate solutions within this population are evaluated using the fitness function. In this case, the fitness function is the function itself, the function which we want to maximize. That particular function itself is the fitness function here. So we evaluate the fitness function. Then the fitness of this particular each individual will be good. That is, it is considered to be most fit if the fitness function, the function value is higher in this case, since it is a maximization problem. If the fitness function is evaluated to a larger value, that is considered to be a better fit individual. So then while we consider t is less than or equal to 4000 minus p. This is taken as 4000 minus p is the value, the what you say. Actually, this p is not required here. P is since we have to evaluate up to 4000 generations, we have to generate up to 4000 generations. That is why we are taking 4000. T less than or equal to 4000. Minus p means there are p individuals. Since in each generation there will be p individuals are one generation, one new individual is generated. In each of the iteration, one new individual is generated. We have to evaluate a total of 4000 individuals also. So initially we have p individuals already here. The initial population, there are p individuals. So we evaluated p individuals here. So we have to evaluate 4000 minus p individuals now, in order to evaluate a total number of 4000 individuals. That is why here is 4000 minus p. So we repeat these steps for 4000 minus p number of times. So then suppose p is 10, that is our population size is 10. When population size is 10, p is taken as 10. That is when you initialize the population, you are generating only 10 candidate solutions. Then you are evaluating the 10 candidate solutions. Since already 10 candidate solutions are evaluated, now you have to evaluate 4000 minus 10, that is 3990 more populations. Not population, individuals. So we have to generate that many individuals more. So what we do is we select a parent. A parent can be taken as X mom, Y mom. That is, this X and Y together constitutes a specific candidate solution. So this is the mom. It is taken randomly. Then we select a second parent. Again, it is called as dad. That is X dad and Y dad. Then we create an offspring using any operation between these two conditions, these two X mom, Y mom, and X dad and Y dad. So an X kid, Y kid is formed. So it is something like this. X kid and Y kid is found out something like a random value between X mom and X dad, plus any constant for nx in between this 0 and sigma. Sigma is some standard deviation of this available population, the x values of the available population, standard deviation of the x values of the available population. So that is a method of finding out or creating an offspring. It may not be always like this. You can create or you can find out your own methods for creating a kit. So X kit and Y kit is also found out. So using these two chromosomes or these two individuals, we found out these two, the new offspring. Then we find out the fitness of the kit. The fitness of the kit is found out. In the next population, the population T plus 1, we remove the worst solution within this solution with the kit. The worst solution is removed and the kid is added to the population. So if the kid is the worst thing, then we discard it. So if the fitness of the kid is not good enough, then we can remove that one also. So that is it. So we replace the worst element or the worst individual in the population with the kit. Now we increase the generation by 1, that is T equal to T plus 1. So this process is repeated till this T becomes equal to 4000 minus P. So that many times, that many values are checked. So this is how a problem is solved using. It is only the basic introduction to evolutionary computation and only a basic example is also, a simple example is also shown. How to solve a simple example using evolutionary computation. That is what we have done. And the one of the difference between this evolutionary computation and the genetic algorithm is that here, see, in this case, only one kid is generated. One offspring is generated here. But in some cases, there are multiple kits are generated. That is, not just one offspring creation procedure is done in a loop. A number of offspring creation operations are done. More than one kid is created during the same iteration. So in evolutionary computation, most of the evolutionary computation procedures, only one kid is generated in an iteration. But in the genetic algorithms, a number of offsprings are generated in one iteration. That is the basic difference between the genetic algorithm and evolutionary computation procedure. And obviously, in genetic algorithm, there are other offspring creation operations also, like crossover as well as mutation also. Then inversion is another procedure through which this new offsprings are generated.